All right, welcome everyone. Good morning, good afternoon, or good evening, wherever you might find yourself right now. We've had a lot of interesting talks already. I wanted to go into a different direction and talk about how CST Studio Suite can help you with simulating devices from small consumer electronics to relatively large computer servers that you would typically place on a data center rack with regard to thermal. So let's get going. As we know, electronics are everywhere these days, and really everywhere. From the smallest gadgets in our daily lives, such as smartphones, smartwatches, and what have you, to computers, and the tons of electronics that control our cars, our robots in the factories, and so on. We meet electronics everywhere, and devices are getting increasingly sophisticated and complex. They're getting lighter, they're getting smaller, they get new features with every release, and consumers are getting to expect this. And if you want to differentiate yourself from the market, you have to give high quality products that are reliable and long lasting. So how can we do that? In the movie Minority Report, Tom Cruise showed us even fancier electronics. It's over 20 years ago already. Unbelievable. The fact that the movie was 20 years ago, I mean, not the electronics. But that's not what we want to talk about today. What we're interested in here is the parallels we can draw, because in Minority Report, Tom Cruise was able to visualize what hasn't happened yet, to use his knowledge to prevent stuff from happening, to see the unseeable. And we need something like that to see the unseeable, to help us with the electronics we see today, to understand, innovate, design, and prevent problems from happening. But there is good news to be had. CST has been doing exactly that for the past 30 years through computer simulations. We are able to allow designers and engineers to visualize the invisible, to see what's going on. For example, here on this 5G phone, we can make them see the unseeable and imagine the unimaginable. Well, so far we've seen the field plots of the electromagnetic field patterns here. However, as you will be aware, most electronics devices also come with thermal problems, and cooling them down properly is a challenge in and of itself. And CST forges a connection between the electromagnetic and the thermal world. And I would like to show you how you can use CST Studio Suite to do exactly that, to forge such a connection. Well, here we can see an overview with some of CST electronics cooling features. So we have a lot of them, and we can talk for a long time about them, and but we only have half an hour after all. So I don't want to go through them bit by bit, but rather figured we can maybe demonstrate a bit by going through a number of examples. And the first example is a smartphone to demonstrate the EM thermal link, GPU computing, and ECAD file import, a full simulation of a PCB. So hopefully using this example, which I said is a smartphone, we can address one of the questions: how does it work? Let's take a look at the device first. So this is our 3D experience phone, which we have developed in order to demonstrate workflows and simulation techniques. So it's been developed by us. No worries for all the phone designers out there. It's a fully featured phone though, so with, in general, all the features that a real phone would have as well. Among these is a host of antennas, which in this instance I don't want to dive into. But look at thermal aspects. Besides the antennas, we have plenty of other parts as well, of course. The battery, camera, smaller PCBs to connect the connectors, the motherboard, and so on. Demonstration-wise, we have a fully functional phone at hand here. Let's take a quick look at a video which demonstrates how we can evaluate and explore the thermal side of this phone, CST. So we can store the PCB in an ECAD format. We can keep it on a 3D experience platform, or just have it available on the hard drives. Both options are equally fine. We can easily load the PCB data to CST Studio Suite, and there we can simulate the PCB and get a first idea for what kind of heat sources we have here by running, for example, an IR drop simulation. This way we can get the losses on both the chips and also on the traces in the PCB. After this is done, we set up thermal simulation, directly have heat sources available already, those that have been pre-calculated in the IR drop simulation. And at this point in time, we can import the rest of the smartphone, or the other details like the camera, the casing, screen, and so on, and use these shapes in order to assign further heat sources, which should be considered in the simulation. And afterwards, we run through the usual simulation steps, of course. So take care of the mesh, set up the boundaries, and so on. In this case, the meshing is an octree hex mesh for the CHT solver, for the heat transfer solver, and we're sending it off to be calculated on remote computer at the moment. Let's pause here for a moment. So the meshing time takes about 5 minutes for 80.5 million cells, 8.5 million cells, and total simulation time is about 77 minutes on the GPU Quattro RTX 1000. So the GPU card, okay card, it's not top of the line, but it's okay. And once we have the simulation done, we can of course take a look at the results. For example, the temperature might be of interest if we're looking at thermal management. What else? For example, the streamlines, so the way the airflow, how that looks like. We can visualize this in CST, and we can also take a look on the 3Experience platform, upload results, and preview there. So we have a lot of options available, and overall, I think it's a pretty cool workflow that we could see here to simulate thermal distribution of a smartphone like this. So we could easily set up the simulation. We could automatically set up a large number of heat sources, add further details and sources if necessary, set up the mesh, send it off to solving, and so on. And the nice thing about the workflow is that we don't just assume power losses for the most part. We are actually using data from the IR drop simulation as excitation sources. So what we can see here on the screen, you can see the power losses on the traces and the power nets. And this distribution is also used as a source for the thermal simulation. So this allows for a high degree of accuracy, because we can take into account losses that would otherwise be maybe forgotten or overlooked or guessed at wrongly. Yeah, this is especially important when things start getting really complicated. We would otherwise have to track and remember a lot of further detail. Speaking of detail, so very nice details come up concerning the details on the board itself and the degree of control that we have here. So the simulation we saw earlier, that included the whole PCB, the traces and everything included. But we can also do a bit of averaging here. So for example, we can average layer-wise, which means that each layer in the PCB will be averaged separately. So we'll be zooming in here in a moment, and then we can see all the individual layers. Or what we could also do is to average everything. So we get one block of material, which is anisotropic, thermally speaking, of course. And this makes sense, especially if you want to get a quick preview. Maybe you don't have all of the details yet, and you just want to get a quick look at what could be happening. Another nice feature that is embedded here is that we can average overall, but also keep some things actually in detail. So if we're especially interested in a certain chip, but we want to speed things up, we can draw a certain area like you can see here in the video right now, and exclude this area from the simplification process. We just finish the import here. We will be able to see in a moment that we have one material for most of the board, but the details around the chip here are kept. I will see that in just a moment. And we're at 100%. Done. There we go. And yeah, so we can mix however we want to, and have some parts simplified, have some parts detailed, however we want to proceed. And yeah, working without any simplification is probably something you will want to do in the end anyway, just to be sure in the final stages of your design, you want to be sure about what's going on and about the thermal behavior. So just like we showed on the first video, actually. And this used to be quite hard or almost impossible with the amount of details that you would have on the boards. You just ended up with too much mesh for the computer to handle. But in CST, we do have the capability to let the mesher determine the volume fractions which are present in the cell. And from this information, actually create a mesh which has the correct thermal behavior for each mesh cell. This simply runs in the background without any interaction with the user necessary, although you can, of course, set some guidelines regarding the degree to which you want to split up the cell in itself for this. And this is a technology that can handle not just PCBs, but really any model that you want to use in and one last thing regarding the level of detail that is being used. So we can automatically generate these simple blocks for the heat sources based on the footprint information available in the ECAD model. However, if the corresponding information is available, we can also go a step further. So we could, for example, not use a brick, but a 2R model, a 2-resistor model, where we have 2 thermal resistors, or even a more complicated network of thermal resistors, like the Delphi model. The Delphi model, coincidentally, also includes capacitor, so thermal capacity. And this is quite useful if when you want to run transient simulations as well. So far, so good. We have seen we can easily use CST in order to simulate complex models. But the question that might come up is, can we trust the simulation? Can we put our faith in the results? Obviously, the answer is yes, but let's see. This example is rather simple compared to the smartphone that we had before and that we could see earlier. So it's a DC-DC converter with a very straightforward simulation. First, you run an IR drop simulation, then thermal simulation, losses from the chips are automatically taken over, and the board is simplified in this case. So see, the heat sources are automatically transferred. The heights still need to be set, though, although that could also be part of the ECAD file. In this case, we're working with a completely simplified model of the board. And when this is simulated, it runs on a regular laptop in about 20 minutes. So you very quickly get a good idea for what's going on. You can nicely see the thermal behavior here, the temperature, also the temperature, is it the heat plume as it goes into the air, and visualize also the flow pattern that we have in the air here. Nice thing about this model is that we actually built this. My colleague, Marcel Plonker, also measured it, both electromagnetically and thermally. So I don't want to go into too much detail. We do have a blog post on the topic, though, so we'll be posting that also with the recording of the video. So please go ahead if you're interested. Take a look at the blog post where you can find more information, just a little bit more on the topic. Just to recap what was done here. The ECAD data was imported, used for an IR drop simulation. Then we performed a thermal simulation with the resulting losses. We also did a 3D EM simulation. Because with the IR drop, we can, of course, not take into account switching losses. So then another thermal simulation was run with that 3D EM simulation and the transient task that was run in there. And the case including switching losses was indeed very close to the measurement results, despite the simplifications used on the board in order to allow for a fast evaluation of the temperature. As I said, we will link the blog post also in the community, so if you're interested, go ahead and take a look. Anyhow, I think it's a nice proof of how simulation can be used to suss out the thermal behavior of a device, what it will be like, and how we can use it to predict the future behavior and make the unseen seeable. Another question that might come up is connecting to thermal sources from a 3D simulation. We've already seen the value, I think, in connecting the physics in the previous examples, but we haven't really explicitly taken a look at connections to 3D simulation so far. So what we have here is a 5G base station. We have an enclosure with an array panel built in and some electronics in the back. And let's take a closer look at the antenna. So here we have it. Operates at around 3.6 gigahertz and is something we could find in a 5G station. On the left-hand side, we can see the far field, so here. And on the right-hand side, we can see the electromagnetic field. One thing to note, sorry, just a moment. One thing to note is that the E-field distribution on the patches mostly looks fine. So it's well distributed. We're not expecting any trouble here. Obviously, the redder it gets, the more field we have, the more power also goes. If we take a closer look, it gets quite obvious that the delivery network seems to show a high concentration of field. So if we take a look here, this area looks suspiciously red. And let's take a look here at the map of hotspots, and we can see we have an area with higher loss here. This actually means also we already get a lot of information about where we might expect trouble even before running the thermal simulation itself. So I think these results from the EM simulation are an important step also when it comes to thermal management, that we can, even before we run a thermal simulation, see where high losses will occur, what kind of materials are around there, and this might already suggest solutions to deal with any problems that might come up. And interestingly, yeah, the actual antenna elements are likely to be less of a problem here compared to the feed network, as we already discussed, as we can also see here right now. So this section of the network may be quite sensitive to heating, and makes sense to take a closer look at this area. So the feed network before the power is split up into the subarrays. Why is this problematic? Okay, we have temperature, sure. What does that mean? We could have some detuning, we could have material properties changing, and if it gets especially hot and we have some hot-cold cycling, that also means we have thermal stress or mechanical stress caused by the thermal cycling. And overall, it behooves us to make sure that the temperature doesn't get too high. So how do we go about the simulation? Well, first, probably makes sense to take a look, how high will the temperature actually go if we simply put the antenna into a closed system? In this case, we'll be using the CHT solver again, so conjugate heat transfer solver, and we need to take some care with the meshing, make sure that the traces are resolved in those areas of high power loss as well. This actually works very nicely with the hexahedral meshing, and with the octree hex mesh, we're able to refine where it's needed, as we can see very nicely on our slides over here, and also make sure that the accuracy is not compromised. So the CHT solver uses the so-called immersed boundary technique, which we can think of as something like PBA, perfect boundary approximation, for CFD. Yeah, so closed off, passively cooled sealed enclosure like this is probably quite appealing on some level. I mean, with the enclosure, we can make it watertight. We can make sure that no dust goes in there, no other particles go in there. And in the simulation itself, we can nicely see where we're including almost heat transfer here. So we have conduction in the material itself. We have convection with the air inside, with the air around it. We also have radiation. And well, radiation is something that should definitely not be neglected. I see this sometimes, especially when we're coming from an EM background. It seems easy to forget, but when we're talking about natural convection, as we are in this case here, radiation often accounts for like getting rid of half of the losses. Anyway, we can intuitively already see that the sealed off behavior is maybe not ideal for thermal. And indeed, the hot air is trapped in there, the streamlines are circling around. So what do we do? We could, for example, do forced cooling by adding 2 fans with 100 CFM each. Would that be enough? At the top, we are adding a grill here. This is just modeled as a flow resistant sheet. And it has very nice results. We can see a 27 degrees Celsius reduction in the temperature. Okay, so this is with 2 fans, but you really need 2 fans, not just 1 in there, so we can easily play around with the model a bit, see what would happen. And there is, again, a very nice flow in the system. And if we look at the temperature, we can see it performs very well and carries away the heat nicely. And we have, again, 26 degrees Celsius temperature reduction. So 1 fan would certainly be enough. That being said, fans can also bring problems of their own. It's another component in the system. It must be contained. We suddenly have moving parts in there, and so on. So what about a simple case of passive cooling? We're just adding slits in there. Intuitively, it's clear an opening should already help to lower the temperature. In this case, we're talking natural convection again. So it probably makes sense to model the area of the slots explicitly instead of relying on the on a flow restriction sheet as we did before. And we can see the airflow very nicely goes through, is pulled in, exits there, will carry a lot of heat with it, of course. A few streamlines stay in there, but that's okay. The most part actually escapes and is able to carry away the heat, thus avoiding the heating up of the antenna. And yeah, this leads to a solution that might just be adequate for the application. Temperature is not low as in the forced convection case, but it's reduced considerably without any additional parts that we have to add into. And we also don't have any moving parts or so in there. Now, this is a relatively large enclosure. And with 3.6 gigahertz, we're at a relatively low frequency. What about higher frequencies? There, it gets a lot more critical. If the frequency goes up, lengths go down. So if we go to something like 28 gigahertz, we're like maybe 7 to 8 times smaller in length, which means in the area, we're already like 50 times smaller. And with that, everything gets much more sensitive. Even with a much lower input power, we get smaller, but also faster and much, much hotter and much more sensitive. And at this point in time, it might make sense to bring in some more advanced cooling techniques, such as maybe heat pipes, liquid cooling, thermoelectric cooling. Think about other thermal interface materials. And well, CST got you covered. You can do all of that if you want to. So it might be more expensive, but it's a much more effective cooling system, of course. So we can see nicely here that including this cold plate with simple water cooling, able to bring down the temperature a bit. And just the final comment, the accurate loss mapping is really important in this case, simply because of the thermal fatigue, which will come up because of also the temperature gradients that we see. So the close connection that we can easily establish using CST is critical for many phenomena if we accurately want to marry the different physics. I'm running out of time, so I'll be a bit quick now with the last example, which is where we're looking at something a bit bigger, namely a server. But the geometry itself is from an open source project, the Open Compute project, and the geometry was downloaded from a sub-project there, Project Olympus server, and we just imported it to CST. We can see we have a high degree of complexity. We can see a hard drive, the CPUs, plenty of memory chips, the motherboard. More interestingly, it also carries some heat pipes in the middle and some heat sinks with very thin fins. And so how was this prepared for the simulation? We have an amazing level of detail here, and that detail was mostly kept. I think in the past, there would have been a lot of simplification going on to model something like this, but that also sacrifices accuracy. It also sacrifices time. We need a lot of time to do that. And in CST, we can deal quite efficiently with the geometry. So a little bit of simplification was done. For example, the fans were originally actually modeled with blades. We don't do that in CST. We use an equivalent fan model. And so this was just replaced by brick-like structure. And most of the time went into material assignment. Actually. So we assumed some heat sources, set the fans, And the next part was already looking at the mesh, and we have around a mesh count of 30 million here, meshing time of a bit over 16 minutes. And we can see how nicely the mesh confirms to the geometry. Case of the fins of the heatsink, the baffle here, and also the screens where the air must go through. And by putting this effort onto the computer for simulation and first upping the mesh, we have saved ourselves a lot of work of this. The analysis was carried out on a relatively old Xeon machine with only 2.4 gigahertz and 40 cores and a relatively old GPU card. You could expect better results with the newer card. But anyway, even so, it was around 21 hours. So you can set it up on one day and already look at results on the next day. And I think the results look quite nice here. We can easily see the streamlines going through, even see some unexpected streamlines in this corner here, which we'll talk more about in a minute. Of course, we're more interested in the temperature in the end. The temperature looks fine in this case. Don't have that large power levels, and the heat pipes are very efficiently at distributing the heat in the model. So in this case, it's actually quite interesting to see that the fins of the heatsink are actually quite hot compared to the rest of the model here. And yeah, the memory usage is also fine, I think. There was some maximum memory usage at the beginning, but that quickly went down to 76 gigabyte for the of memory for the actual solver run. And like I mentioned, there was a small surprise here. So we didn't actually put anything into the PSU unit. There was some very small details here, some small areas where air was then sucked in and just went through here. And this was already picked up by the solver. And it's really nice to see how these tiny details are already uncovered in the simulation. And just opens up the the possibilities that we're getting, especially as the models get more sophisticated and more complex. And so it's good to see that we can give this over to the software to take care for us instead of us having to take care of it. Yeah, I hope I was able to demonstrate one thing in this presentation. CST can be used to build bridges between the different physics, so that maybe CST is the bridge, however you want to see it, to connect, for example, the EMAG and thermal worlds. There's a lot of things I wasn't able to spend much time on, like how the heat pipes are set up or the cooling fluid simulation, but I hope it was clear that CST offers the tools to help engineers, physicists, and designers to really see the world with, and to see the effects that we don't usually pick up on. That with simulation, we can make visible the unseeable and predict the future, at least with regarding to the behavior of the devices we are developing. So we can all be like Tom Cruise in Minority Report, only with regard to thermal management instead of homicide. Yeah, thank you for listening, and I hope you all enjoyed the presentation.